All right, well, what I was going to do was some exercises using the method of characteristics. But if there are any questions before I do that, I'm happy to answer them.
Morning, Professor. Can you do from the homework 8? Uh, mm, Page 25, and the exercise number 5. Just for the home 8.
Okay. Just a second. Okay, so that's good. Let me, so this is in Logan, page, page 25, sorry, which problem? 5?
Right, 5.
Number 5. Okay, so we have the initial value problem, u sub t plus xt u sub x equals 0, and some initial condition, u at times 0, u of x at times 0 is f of x. So if we use the method of characteristics, what we're multiplying u sub x by is xt. So let's try to solve the differential equation dx dt equals xt. So this is separable, 1 over x dx dt equals t, or the integral 1 over x dx is the integral of t dt. So we get that the log of the function x is a half t squared plus some thing which is constant with respect to t. I'll just write 1/2 xt squared plus some constant. So x of t is some constant times e to the half t squared. Okay. And then the idea is if you look at the function u evaluated at x of t comma t, if we differentiate this with respect to t, we get the partial of u with respect to x times dx dt plus the partial of u with respect to t. Partial of x with respect to t is xt. So this is ut plus xt u sub x, which is 0, which means u of x of t comma t is constant with respect to t. It's some function, let me call it phi of x. So at time t equals 0, when we let x at 0, just call that x naught. At t equals 0, x naught comma t is phi of x naught, and that's equal to f of x naught. And let's see, what is this constant c? X of 0 is c, which is x naught. So c is equal to x naught. So we have x is x naught e to the half t squared. So x naught is x e to the minus a half t squared. So f at x naught, this is f of x e to the minus 1/2 t squared. So this derivative of x of u of x of t comma t is 0. So it's constant. It has the same value for all t. So in particular, at t equals 0, so u of xt is u of x at 0, which is f of x to the 1/2 e to the 1/2 t squared. So let's just take a look at this. If I take u of xt, so f is some function. It's just the initial value condition. We don't know what f is. It's just some function of x. But whatever that function f is, if we let u of xt be equal to f of x to the 1/2 e to the x times e to the 1/2 t squared, if I differentiate u with respect to t, I get the derivative of, I have df dt times the derivative of this with respect to t, which is x t e to the 1/2 x squared. And the partial of u with respect to x is the partial of f with respect to x times the derivative of this with respect to x, which is e to the 1/2 x squared. So I've lost a minus sign somewhere. That's here, minus. Minus. So this is minus this, and this is correct. And okay. Here, I mean, I did that maybe a little bit too fast, so let me just go through it again. So we start with this differential equation. Ut plus xt ux equals 0. And this is for all x, from minus infinity to plus infinity, and for t greater than 0. So this is an unbounded domain in x. It's unbounded domain. And t from 0 to infinity. So this, and we are only given an initial value condition. So this is an initial value problem. There's no boundary condition. So we let dx dt, we think of x as a function of t, and we solve the differential equation dx dt equals x times t. So when we solve that equation, that's just a first order equation, and we get that x of t is some constant e to the 1/2 t squared. And the constant is x naught, just the initial, the value of this function at x naught. So x of t is x naught e to the plus 1/2 t squared. So x naught is x e to the minus 1/2 t squared. Now, if we look at u on this characteristic curve, x of t, this is a curve, this derivative with respect to t is 0. We basically have this integrating factor, which turns this is just 0. So this is a constant with respect to t. So u of x of t comma t is some function of x, phi of x. What is it? So, and we know that, so this is independent of t. So in particular, when you let t equals 0, phi u of x naught t is phi of x naught. But u of x naught comma 0 is phi of x naught. That's f of x naught. X naught is e to the minus 1/2 t squared. X e to the minus 1/2 t squared. So that's the solution for all x and t.
Professor, which method do you use in that case?
Well, for one thing, this is in the section of the book on the method of characteristics. So you should use the method of characteristics.
Because also okay. Uh, Professor, for homework number 9.
Yeah, just 1 second.
Yeah.
Okay, sorry, go ahead.
Yes. From homework 9, can you do number 5C? Number 5C.
Um,
Yeah. Homework number 9. Exercise 5C.
right, okay, just 1 second. Let me get some clean paper. So this is homework 9, number 5C. Okay. So this is the problem. U sub t plus u sub x equals x, so it's not homogeneous. And we have, and so this is for x greater than 0 and t greater than 0. And we have the initial condition that u of x0 is equal to 0. And we also have the boundary condition that u at x equal to 0 and all time t is equal to 0. So this is some initial condition. This is some boundary condition. So, oh, and we want to solve this using Laplace transform. So if we take the Laplace transform of ut plus ux, that's going to be the Laplace transform of x. Right? So we have to remember or look up, right? Look up what is the Laplace transform of x. And I believe it's 1 over s squared. So the Laplace transform of a sum is the sum of the Laplace transforms. The Laplace transform of u with respect to t is s. The Laplace transform of u minus the initial condition u of x0 plus the Laplace transform of u sub x, which is the derivative with respect to x of the Laplace transform of x. This is really x comma x, x comma s, right? And that's equal to 1 over s squared, 1 over s squared. So I have a differential equation for u. I have that the derivative with respect to x of u of xx plus s u of xs equals 1 over s squared. Oh, I'm sorry. I made one mistake. So, sorry, let me get this right, because this is important. This is the Laplace transform of x. That's the Laplace transform of x times 1. We're taking the Laplace transform with respect to the variable t. So this is x times the Laplace transform of 1. The Laplace transform of 1 is 1 over s. So this is x over s. So what I have here is x over s. Well, that's a first order non-homogeneous equation. If we take as the integrating factor you have an s there, e to the sx. If I multiply through by e to the sx, what do I get? I get e to the sx times the derivative of x with respect of u with respect to x plus s e to the sx u equals e to the sx times x over s. And this is the derivative of e to the sx with respect to x. So this is equal to the derivative with respect to x of 1 over s x e to the sx. So e to the sx times u is the integral of 1 over s e to the times x e to the sx dx. Okay. Let's see. See, so someone just entered the session. So let me just start this again. So this was from homework 9 on the Laplace transform, number 5C. And we have for x greater than 0 and for t greater than 0, there is the differential equation, the partial differential equation, ut plus ux equal x, with the initial condition that u of x 0 is 0 for all x, and the boundary condition that at the left-hand end, which is t equals 0, x equals 0, u of 0t is also equal to 0 for all time. And we take the Laplace transform of both sides. So you get the Laplace transform of ut plus the Laplace transform of ux is the Laplace transform of x. But again, the Laplace transform, this is an integral with respect to t. So this is like x times 1. X is a constant, it's not t. You can factor the x out. So the Laplace transform of x is the Laplace transform of, it's x times the Laplace transform of 1. And the Laplace transform of 1 is 1 over s. Laplace transform of ut is s times the Laplace transform of u minus the initial condition, but the initial condition is 0, so that term disappears. The Laplace transform of ux is the derivative of the Laplace transform of u with respect to x. So we get this first order differential equation for the Laplace transform of our unknown function, the Laplace transform of our unknown function, the solution, derivative of u with respect to x plus s times u is equal to x over s. So if we multiply by e to the sx, on the left, we get the derivative of e to the sx times u is equal to the integral of e to the sx times x over x dx. You can factor out the 1 over s. This is the integral of x e to the sx ds. We can integrate this by parts, x e to the sx 1 1 over s e to the sx. So I get e to the sxu is equal to 1 over s times x over s e to the sx minus this integral, which is a 1 over s squared e to the sx. Plus a constant. So, and then I multiply by e to the minus sx, so I get u of xs is equal to, this cancels, x over s squared minus 1 over s cubed plus c e to the minus sx. Now,
We need to use the inverse Laplace.
oh, I'm not done. Yes, we're going to have to use the inverse, but let me first see if I can figure out what is this constant c equal to. Okay, so c is some constant, but it could be a function of s, right? So I'm integrating with respect to x. This is really sort of c of s, if you like. So if I let x equal 0, u of 0 comma s is minus 1 over s cubed plus c. What is u of 0 s? U of 0 comma s. This is the Laplace transform. This is the integral from 0 to infinity, u of 0 comma t e to the minus st dt. But by our boundary condition, u of 0t is 0. So this is 0. So 1 over s minus 1 over s cubed plus c is 0, means c is 1 over s cubed. So for this differential equation, the Laplace transform of the solution, u of x comma s, is x over s squared minus 1 over s cubed plus c. C I just found is 1 over s cubed, 1 over s cubed e to the minus sx. So then we have to use the inverse Laplace transform to find u of x comma t. So go to our table of Laplace transforms.
Yeah, this is the reason, Professor, I got confused with the constant. Sometimes that constant is always depends on t, or
Well,
can
this
be.
constant depends on s, right? Because here I'm integrating a function with respect to x. So the constant is independent of x, but it can depend on t. It can depend, it's independent of x, but it may depend on s. Okay. All right,
Okay.
let me go find the inverse Laplace transform. So we have from the table, using the letter t, that if you have t to the n, the Laplace transform of t to the n is n factorial over s to the n plus 1. So here I have a 1 over s squared. So if I let n equal to 1 in this formula, the Laplace transform of t is 1 over s squared. So u of x comma t, this is x times 1 over s squared. That's x times t. Here I have 1 over s cubed. In this formula, if I let n equal to 2, I get the Laplace transform of t squared is 2 over s cubed. So the Laplace transform of a half t squared is 1 over s cubed. So this is the inverse Laplace transform of 1 over s cubed is minus a half t squared. And then I have this more complicated expression, 1 over s cubed e to the minus sx. So I look at my table and I see the following expression. So for the Heaviside function h, what's on the table is h of t minus a times f of t minus a. F is some function. This is the Laplace transform of f times e to the minus as. So what I have over here, I have 1 over s cubed e to the minus sx. Let me write that as xs, just reverse it. So if I let a equal to x and capital F equal 1 over s cubed, this is what I get. This is the Laplace transform of this expression. What is this expression? This is h of t minus x, f of, so if f of s, capital F, this is the Laplace transform of a function little f. We already saw that the Laplace transform of a half t squared is 1 over s cubed. So f of s is equal to a half t squared. So what I have here is, oops, let's see, something is not quite right. Oh, yeah, so I want f of t minus a. So my function f is a half t squared. So f of t is a half t squared, but f of, let me move this up. F of t is a half t squared. F of t minus a is f of t minus x is a half t minus x squared. So when you put this together, my function u of xt is xt minus a half t squared plus h of t minus x squared over 2. So that is the solution of the PDE.
So means, do you use the step function definition, right?
Yes,
For the last term, right?
yes.
Oh, okay, thanks. Professor, can you do the last one from homework 9? Is the 6. It's like a proof. It's a proof.
Mm-hmm.
Yeah, this is the last exercise.
Okay.
Thanks.
So remember the definition of the Laplace transform So this is, let's say, homework 9, number 6. The Laplace transform of a function f of t is the integral from 0 to infinity f of t e to the minus st dt. So suppose we replace f of t with a function f of t. So this is capital F of s. That's capital F is the Laplace transform. So what about the function f of t e to the at? What is the Laplace transform of that? This is the integral from 0 to infinity f of t e to the at times e to the minus st dt. That's the integral from 0 to infinity f of t e to the at e to the minus st dt. That's the same as the integral from 0 to infinity f of t e to the minus, just using rules of exponents, s minus a times t dt. And this is exactly this Laplace transform evaluated at s minus a. So that's the whole proof.
Thank you.
Sure. Is that it? What I think I will do, if you're studying over the weekend and you have more questions, our exam is 11 o'clock on Monday morning. Unfortunately, I have another class from 9 to 11, but I can be available on Zoom on Monday between 8 and 9 in the morning. If you have any last minute questions you want to ask. And I may also send out another, just a little review sheet of problems that would be on the exam. No different from problems on the homeworks, just a few more things to practice.
Oh, Professor, also, hello?
Yeah, I'm here.
Yeah, are we going to have an example in the exam having to deal with the convolution product?
Yes.
Oh, we will?
Yeah. Because
Okay.
it's important to know what it is. I mean, it's a basic fact about Laplace transforms that the product of two Laplace transforms is the Laplace transform of the convolution of the functions. So, I mean, it's just a definition. You write down, you do a calculation. On the homework 9, there were a couple of examples of convolutions, and I can do one if you like. But you know, it's a basic. I mean, the Laplace transform is a fundamental method used in solving ordinary and partial differential equations. And when you use the inverse Laplace transform, you use this fact about the convolution a lot. So, yes. But it's just a definition, and then you write it down and you have an integral, so you're reduced to freshman calculus. You're just computing an integral of some function in one variable. So they're not supposed to be hard. You know, I always try to put a couple of very easy problems on the exam, and I would think of the convolution product as a very easy problem. It's a lot easier than solving a partial differential equation.
Okay, all right.
But again, as I say, if you can email me questions over the weekend also, which I can try to answer if I can get it into an email. But I'll also be available on Zoom at the same Zoom address, the same one we use for our classes. I'll make sure I'm online from 8 to 9 in the morning on Monday, if anything comes up at the last minute. Okay, well, if there's nothing else, have a good weekend, everyone, and I'll be back online on Monday morning.
Professor, sorry for the review sheet. You will send the review sheet before the exam too, or?
Yeah, I'm gonna try and I'll spend this afternoon putting together a review sheet, and I'll email it to you this afternoon, late this afternoon.
And then go over on Monday.
Well, if you have any
after
questions, I mean, I'll answer questions about anything on
okay.
Monday. The review
okay.
sheet is just some more practice problems to help you.
Yeah, just to put more characteristics method.
Yeah, that's what I was going to concentrate on, actually.
Yeah, yes, because we need more practice.
Right, okay.
Right.
And
Thank
I'll
you.
make sure
Professor.
that on the review sheet, I'll put the answers so you can, if you do the problem, you can check against the answer.
Oh, okay, great.
Yeah.
Thank you, Professor.
Okay, all right. Bye, everybody.
Take care.
Weekend.
Thank you.